This is the classic food pyramid from the 1990s. For over 40 years, conventional nutrition and medicine relied on models exactly like this, where the primary objective was strictly avoiding toxicity and disease. Today, clinical practice is moving past that floor. Instead of merely correcting physiological deficiencies to keep people from getting sick, researchers and practitioners are attempting to push human biological limits upward. But as we try to push patients past standard baseline reference ranges, a major complication arises. The robust empirical evidence and long-term safety data that we rely on for basic health recommendations rapidly disappear. Without massive clinical trials to guide these higher thresholds, the pursuit of optimization currently falls back on subjective tracking. Patients self-report their perceived well-being, their sleep quality, and their mood, which turns out to be a flawed metric for actual physiological progress.
Effective monitoring of these gains depends on our ability to distinguish between interventions backed by objective human efficacy and compounds that primarily target a patient's perception of their own performance. To understand what high-quality human efficacy actually looks like, we can look at bedrock compounds like creatine and omega-3 fatty acids. These interventions possess decades of longitudinal safety data across highly diverse populations. We know, for instance, that you can administer high doses of creatine to frail older adults with essentially zero adverse side effects. When a compound has been proven safe at that level, experimental dosing carries minimal clinical risk. If a practitioner attempts to push a patient's omega-3 index from an 8 up to a 12, the specific efficacy of that higher dose might be unknown, but the safety profile is completely secure. Recent trends in biological optimization operate very differently. We are seeing entirely novel molecular structures being adopted by the public without any foundational human efficacy trials. In this modern optimization culture, users are looking at a lack of immediate documented adverse events and dangerously conflating that with proven long-term safety. The catalyst for this shift in how people administer new compounds can be traced directly to this box. This is Mounjaro, one of the mainstream GLP-1 agonists. Notice the specific labeling for subcutaneous use via pre-filled pens. The overwhelming weight loss efficacy of drugs like tirzepatide for weight loss completely dismantled traditional needle phobia. Millions of average patients became entirely comfortable injecting themselves on a weekly basis. That newfound behavioral tolerance effectively removed the psychological barrier to subcutaneous administration. In doing so, it inadvertently created a massive bridge to a shadow market of non-FDA-approved peptides. The primary drivers of this secondary market are compounds like BPC-157, which users inject for theoretical structural tissue repair, and GHKCU, pursued heavily for its reported cosmetic benefits. Unlike the GLP-1s that paved the way, these unregulated peptides operate in a clinical void. Outside of a few specific sarcopenia secretagos, these compounds possess near-zero human clinical trials for their desired effects. Yet otherwise highly cautious adults are aggressively utilizing these compounds, basing their health decisions purely on anecdotal promises rather than objective physiological tracking. By removing the simple friction of a needle, the widespread success of GLP-1s normalized a culture of biological experimentation that operates almost entirely in an evidence vacuum. This disconnect between perception and evidence becomes even more pronounced when we look at the central nervous system, specifically how individuals attempt to track and optimize their cognition and neuroplasticity. Under normal conditions, subjective feeling, how motivated an individual reports feeling, is a reliable predictor of their objective physical performance. The metrics move in tight correlation. When a central nervous system stimulant is administered, that correlation severs. The subjective readiness score spikes upward. The stimulant artificially elevates perceived capability, inducing false confidence. But simultaneously, their objective output drops, moving in the exact opposite direction.
We see this clearly in objective data from complex working memory assessments, specifically the NBAC task, where subjects have to track and recall specific sequences of stimuli. As the cognitive load scales to higher complexity, like an N3-BAC task, subjects operating under stimulant protocols demonstrate significantly higher error rates and highly degraded reaction quality, despite feeling focused. This specific subjective-objective dissociation is heavily driven by exogenous pharmacological agents like methylphenidate, the active ingredient seen here in Ritalin, particularly when taken by individuals who do not have clinical ADHD. We see an identical behavioral parallel with cannabis use. Users frequently report a state of heightened creativity, only to find that their ideas objectively fail under rigorous review the following day. Exogenous stimulants generate a powerful neurochemical illusion of competence. They make the user feel optimized, which renders self-reported data functionally useless for tracking true cognitive improvement. Learning and memory formation have a strict biological prerequisite. To open the window for neuroplasticity, the brain requires elevated systemic arousal and alertness. This strict requirement is precisely why exogenous stimulant use is so appealing to anyone trying to engineer their own cognitive performance. By introducing these compounds, users are attempting to pharmacologically bypass the body's natural arousal pathways, hoping to artificially force that window of plasticity open. This bypass creates a specific interference. While it successfully primes the brain for alertness, it simultaneously degrades the complex working memory networks necessary to actually encode and retain any new data. This sequence shows the efficiency of our endogenous arousal mechanisms. When the body generates arousal naturally, it triggers a synchronized rhythmic wave across the synapses. Generating that arousal organically releases the correct biological ratios of epinephrine, norepinephrine, and dopamine, perfectly priming the system without overloading it. The brain's neuroplasticity mechanisms require an incredibly precise neurochemical environment. As of right now, only our endogenous pathways can accurately provide that environment without inducing severe cognitive trade-offs. Physical exercise remains the most reliable, thoroughly evidence-based tool we have for generating the required endogenous arousal to achieve neuroplasticity. The exact modality of the exercise, whether you are running sprints, pulling heavy deadlifts, or simply doing jumping jacks, is entirely secondary to the physiological outcome. The physical exertion itself systemically triggers the exact catecholamine cascade required to set the stage for optimal learning. If we return to our tracking model, we see that endogenous arousal generated by exercise does not dissociate feeling from performance. When a user feels optimally aroused after a workout, their performance on complex cognitive tasks like the NBAC test objectively matches that positive, highly motivated feeling. Exercise functions as a proven non-pharmacological lever. It effectively opens the plasticity window while strictly maintaining the integrity of the body's natural feedback loop. Across all domains of biochemical optimization, the core engineering problem remains the same. We have to distinguish true biological signal from subjective noise. Relying purely on the absence of documented side effects, as we see in the unregulated peptide market, or chasing chemically altered subjective feelings with stimulants, introduces fatal noise into any optimization model. The gold standard for biochemical optimization is a closed-loop system. It requires objective biomarker testing, the targeted evidence-based intervention, and then rigorous objective retesting. Whether a practitioner is attempting to push an omega-3 index upward or seeking elevated cognitive focus for a patient, the biological system must be guided by measurable, objective realities. Genuine optimization is not found in adopting experimental compounds that simply alter our perception of success. It requires evidence-backed interventions that objectively elevate our baseline capabilities.